Hello, everybody. So I'm on page 45 in the guided notes, and I want to just introduce gas stoichiometry to you. Now, let's be real here. Gas stoichiometry isn't anything different than what we've been doing. When it comes to stoichiometry, it's all simply about the mole ratio and nothing more. When it comes to gases, though, we're just calculating moles in a different way. We can use the ideal gas law to calculate moles. That's all that's different, and quite honestly, we don't really need to call it anything different. Now we're dealing with gases where we weren't dealing with gases when we first started working with stoichiometry. Okay, so anyway, I'm going to work through a couple of these with you guys, and hopefully, working with mole ratios is going to come back to you. Anyhow, let's get started. So, I'm just going to start with number one. So, here we've got ethanol combusts to form carbon dioxide and water in the following reaction. And, oh, interesting. I just realized it's not balanced. So I'm going to balance this equation and then I'll get right back to you. All right. I believe that this is now a balanced equation. So what are we going to do here? The question is this. What volume of carbon dioxide is produced if the combustion used, okay, so in this reaction, we're using 58.5 grams of ethanol, and it's taking place at this pressure at 2.26 atmospheres at 40 degrees Celsius. All right, obviously, in order to do stoichiometry, we need to be dealing with moles, so let's convert grams to moles. Okay, so the molar mass for ethanol is 46 grams per mole. We're given 58.5 grams. That's going to be 1.3 moles of ethanol. All right, now remember about stoichiometry, right? What is the mole ratio between ethanol and carbon dioxide? Carbon dioxide, by the way, is what we care about in this reaction. We're being asked what volume of CO2 is produced. So let's find out how many moles is produced. Now, if this is 1.3 moles of ethanol, then the amount of CO2 that's going to be produced is going to be 2 moles per every 1 mole of ethanol. So we're going to take 1.3 moles and multiply it by 2. So again, because the mole ratio is 1 to 2, whatever number of moles of ethanol we're going to use, we're going to make twice that of CO2. So we're going to make 2.6 moles of CO2. We're assuming that there's an excess of oxygen because nobody told us anything about oxygen. So we're assuming that we've got a room full of oxygen. So the reaction is limited by how much ethanol we have. All right, so we're going to make 2.6 moles of CO2. All right, now the question is how many liters of CO2 is that going to be? And we are at 2.26 atmospheres and 40 degrees Celsius. All right, so of course we need to convert Celsius to Kelvin, so we did that. We're going to use this R value. The ideal gas constant is going to be 0.0821 because this is the R value that corresponds to working with atmospheres of pressure. Okay, the rest is just algebra, and boom, we've got our volume. It's 2.93 liters. Let's try another one. Okay, in this problem, we got to be careful about a couple of things here. First off, we've got to be aware that we're collecting 265 milliliters of oxygen. So we've got to be careful about that. Also, we're being given a pressure in millimeters of mercury. And I'll be honest with you, I haven't memorized the R value for millimeters of mercury, or working with pressure in millimeters of mercury. So what I'm going to do instead is I'm going to convert millimeters of mercury to kPa, all right? And then we can work from there. This is 10 degrees Celsius, so we'll need to convert that to Kelvin. So there are a few things. This is a balanced chemical equation. This is not barium oxide. This is called barium peroxide, which doesn't mean anything to you probably, but when I looked at this, I was like, oh, wait a second, that's not a correct chemical formula. Well, it is correct if this is a peroxide, so let's not worry about that. Barium peroxide is going to break down spontaneously to form barium oxide and oxygen. So we're going to find out what is the mass of barium peroxide that we need to make the amount of oxygen that we're being told about here. So let's work this out. I'm going to do a couple of conversions, and I'll be right back. Okay, so what I've done here is I've converted to kilopascals. Why? Because I forgot what the R value is for using millimeters of mercury. So what? No big deal. I just converted it to a different pressure unit. I converted 10 degrees Celsius to Kelvin. We are now going to use PV equals nRT. Now, also, let's be careful. We were given 265 milliliters. That's got to be converted to liters, so that's 0.265 liters. If I do all of the math, and by the way, this is the R value, where we're using kilopascals for pressure. Okay, do the math, do the algebra, we get this many moles of oxygen. It's a really small number. No big deal. Now, looking at the equation here, so for every one oxygen, we're going to need 2 barium peroxides. Okay, so the mole ratio that we need is going to be 1 to 2. That means the number of moles of barium peroxide is going to be this, 0.0222 moles barium peroxide. All right, now what we need to do is find the mass of that in order to solve this problem. All right, so the molar mass of barium peroxide is 169.3 grams per mole. All right, so converting moles to mass, I got 3.76 grams of barium peroxide. All right, I'll leave it at that. We just solved 2 of these problems. If you need more help with this, I think I'll make yet another video. But for those of you that are feeling ready at this point to turn away from the video, I think I'll just stop the video right now. But I'll make another one. And if you need even more help than that, please come and see me for a little extra help. Maybe that's all you need. But anyway, hope this was helpful. Thank you. See you in class.